Now next video will be on odd parity bit generator. Now we were already discussing with the even parity generator where we said that in case of even parity generator we have seen that this will be my truth table, this is my K-map, this is the way how I found out the expression or Boolean expression, and this was my logic diagram. And I was saying that if I find out the output response of this final XOR gate is PE, means even parity generator, just the NOT gate of even parity generator will give me an odd parity. That means the complement of my even parity gives me an odd parity. Now how to show that? In that case we will be again using 3-bit numbers A, B and C, another digit for P, O as odd parity. So again we write down 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. These are the 8 numbers, and we need to find out the odd parity. Now initially when we use the first one, it is 0, we see that does not have any 1 present here. That means it's neither 0 nor 1. So we do not have to make it as even, because we are considering here as odd parity. So to make the number odd parity we need to add 1 here. This will give me an odd parity because I have only odd number of ones present. For second one, this is already odd, this will give me 0. Third one is already only 1 is there, so it's 0. Final one, number 3, we see 2 ones are present here. So to make this odd we have to use one odd under odd parity to make the number of ones as odd number. Next, this one is already odd number of ones here, so it's 0. For this one I have even number of 1. To make it odd I put 1 here. Then for the next one we see already even number of 1 here, so to make it odd we have to use 1. And finally this 3 is already giving me odd number of 1, so it's 0. Same way as that of even parity we need to design the K-map, and I already know we are using here 3 variables, therefore we will be getting 2 to the power of 3 means 8 cells for K-map, and we will be numbering them as 0, 1, 3, 2, 4, 5, 7 and 6. So these are the cells given, and we need to number those which is considered here as 1. So cell number 0, cell number 3, cell number 5 and cell number 6. So what do we see? The one which we had in even were 1, 2, 4 and 7, and the one which we are getting here will be what? 0, 3, 5 and 6, which means that just the opposite of even. So now if I find out the expression, we'll write here A bar, B bar, C bar. But before that let me write down here to make you understand better. So here for the first one, A bar, B bar, C bar. Next this one will be A, B bar, C. Then for this one, A bar, B, C, and finally A, B, C bar. So from here let me take C bar as common and write down A bar, B bar plus AB, and within this two take C as common, A, B bar plus A bar, B. This will give me C bar and X NOR, and this will give me A XOR B. So if I consider A XOR B to be as X, therefore this will give me C bar, X bar, C and X. So what do we get here? This is what? C X NOR X, where X NOR is nothing but A XOR B. C X NOR A XOR B is the ultimate expression of my odd parity. So to make the logic diagram, again the same way, we have A, B, C. So first we'll take up A XOR B, and then X NOR. So this added up with C in the form of X NOR to give me the ultimate answer, which means we already had 2 XORs for even parity, and just the NOT gate of the last XOR gate of even parity will give me output as odd parity. Same thing here, if I use one NOT gate just before this XOR gate will give me an odd parity. Next, we'll move on to the parity checker. Now, parity bit checker, rather the parity bit checker diagram is common to both even or odd parity. Suppose if I have 3 bit operations of an bit parity bit, so this will be the way how we operate. This is A and B. A XOR B, this output of XOR gate will be again XORed with C, and finally the output of this will be XORed with, suppose if I initially consider even parity, with even parity, and what I said that just modulo sum of the even parity, modulo sum of the numbers in the form of a XOR gate, if becomes equal to 0, then the answer will be no error. So if I consider this as my table, if I consider this as my table, and if I choose this number, so what do we find out here? This is my A is 0, B is 0, C is 1, and even parity is 1. So what do I get here? 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 1, 0. So when I use even parity and after this modular sum of all this XOR gate, the output of this becomes 0, then I consider it to be no error. Same way, if we need to perform for the odd parity, the diagram will be same in case of even parity. Again, if I choose, suppose these two are my A and B, and this will output of this XOR gate, I will be using it with the third bit, that is C, and then finally of this one will be added up with the output or the odd parity bit, and the output should come here as 1, because as I already know that this complement of this one will give me the odd parity, so the answer should be equals to 1. So similarly way, if I use the truth table of my odd parity, what do we see here? We see here, if I consider this number, supposing if I consider this number, so what do I get here? A is here 0, B is 1, C is 1, and P is also 1. So 0 XOR 1, 1, 1 XOR 1, 0, 0 XOR 1 is 1. So when we choose a certain number on the truth table which will give me odd parity equals to 1, and if I find out the modular sum of all these bits including the parity bit using the XOR gate, if the output for the odd parity bit comes equal to 1, then we consider that there is no error received, or rather there is no error present in the receiver, which means the receiver has received the correct data which is being transmitted by the transmitter through transmission line. And if this would have been 0, then we would have considered that the number is creating an error, which means any one number has been interchanged from 0 to 1 or 1 to 0, which is creating an error. So same thing which we see here, that parity bit checker will be having the same circuit diagram, but only one thing has to be kept in mind, that if we use an even bit parity number, then if I use this particular circuit, the modulo sum of all these numbers, that is in the form of a XOR gate, if the answer of this comes 0 for even parity, then the answer having no error. And in case of the odd parity, the same circuit diagram will be followed for parity bit checker, but the difference is that when we are doing modulo sum of this entire bits using the XOR gate here, and if the answer comes as equal to 1 for the odd parity, then the number is considered as no error. With this, we come to the end of our videos. Hope the video will be helpful for you. Thank you.